The entire universe was once a prison for light. For hundreds of thousands of years, every single photon was trapped, bouncing endlessly inside a searing hot fog. This is the story of the Great Escape, the moment light shattered its chains and the cosmos became transparent. By the end, you will understand the precise cosmic event that allowed light to travel freely, an event whose echo you can still find with a simple radio. What cosmic key finally unlocked the light, and how does its first journey still shape everything we see today? What does it mean for our reality that the universe was once blind? This dense fog was the universe's first and most formidable prison. For nearly 400,000 years, the cosmos was not a void but a searing hot liquid of fundamental particles. Electrons and protons, all carrying an electric charge, swam through this primordial broth. Light in the form of photons was born constantly within this chaos, but it was instantly captured. A photon would zip away, only to be snatched up by a free electron almost immediately, absorbed and then re-emitted in a random new direction. This frantic dance of capture and release happened over and over, trillions upon trillions of times, preventing any beam of light from traveling more than a short distance before being scattered. The entire universe was a brilliant, glowing, and utterly opaque fireball. You could not see through it, not even for an inch. It was a cosmic traffic jam of unimaginable proportions, where matter and light were locked in a violent, inseparable embrace. This state is what scientists call the photon-baryon fluid. Think of it not as a gas, but as a single, thick substance where light and matter are one. The intense heat, far hotter than the core of any star, kept the electrons too energized to settle down. Protons could not catch them to form atoms. This chaos was paradoxically essential. In these first few minutes, this frantic particle soup cooked up the universe's first atomic nuclei, hydrogen and helium, in a process called nucleosynthesis, a key insight from cosmologists like George Gamow. But for light, this same productive chaos was a perfect trap. The universe was a blinding, luminous prison, and its inmate was light itself, bouncing endlessly off the walls of its own creation. The stage was now set, however, for a single, dramatic change that would shatter these chains forever. The universe's brilliant fireball could not rage forever. Its expansion was relentless, and with every passing moment, space itself stretched thinner and colder. In just a few 100,000 years, the temperature plummeted from billions of degrees to a mere few thousand Kelvin, a drop so profound it altered the very fabric of reality. Think of a steaming cup of coffee left on a table, its heat slowly dissipating into the room. The universe was doing the same, but on a cosmic scale, its energy spreading across an ever vaster volume of nothingness. This cooling was driven by the fundamental stretching of space, a process that literally pulled on the wavelengths of light, stretching them out and draining their energy. Particles that once zipped around at nearly the speed of light began to slow their frantic dance. The chaotic roar of the primordial soup quieted to a simmer. This gradual cooling, studied by cosmologists like James Peebles, was not perfectly smooth. Tiny, random variations in density, like invisible seeds, were sown throughout the cosmos, destined one day to grow into the vast cosmic web of galaxies and voids we see today. But for now, the most critical consequence of this great chill was a simple shift in the balance of power. The thermal energy that had once kept electrons and protons perpetually at war was finally ebbing. For the first time, these oppositely charged particles could approach each other without being immediately blasted apart by a high-energy photon. the violent chaos was subsiding, creating a narrow window of opportunity. The first crack in light's prison had finally appeared. This great chill reached its tipping point when the universe cooled to about 3000 Kelvin. At this critical temperature, a fundamental shift occurred, an event cosmologists call recombination. It is a slightly misleading name, for the particles were not reuniting. For the very first time, electrons and protons were able to combine into stable, neutral hydrogen atoms. Before this moment, the intense heat provided a constant barrage of energy, knocking any would-be partners apart. It was like trying to build a house in the middle of a hurricane, but now the storm had finally calmed, one by one, and then in a great cosmic cascade, free electrons were captured by atomic nuclei, settling into orderly orbits. The effect was immediate and profound. The thick fog of charged particles which had scattered light so effectively simply vanished. Where once there was a searing plasma of free electrons, there was now a sea of neutral, transparent gas. The prison bars were gone. For the photons that were traveling at that exact moment, everything changed. Instead of being absorbed and scattered by an electron after a short journey, they simply kept going. They flew forward, encountering nothing to stop them. In an instant, the universe became transparent. Light was finally and irrevocably free. This great escape released a flash of light that still fills the entire cosmos today. We know it as the cosmic microwave background radiation, a fossilized snapshot of the universe at that moment of liberation. It is the afterglow of the fireball, the first light that ever traveled freely, and its journey across space and time began right then. Neutral atoms were the silent custodians of light's great escape. They did not force the prison doors open, but they dissolved the walls themselves. The key was a profound change in how matter interacted with light. A free electron buzzing alone in the plasma was a perfect target for a photon. It would absorb the light particle's energy and fling it off in a random new direction, a process called Thompson scattering. But when an electron settled into orbit around a proton to form a neutral hydrogen atom, everything changed. Its cross-section for scattering, a measure of how big a target it presented to light, collapsed. It became astronomically smaller, almost vanishing. A photon flying through this new sea of neutral gas was like a bird soaring through clear, open sky instead of a dense, blinding forest. It could travel for millions of light years without hitting anything. This dramatic reduction in scattering opacity, a term physicists use for how much a substance blocks light, was the final, silent click of the lock. The universe did not just cool into transparency, it was fundamentally rewired by the birth of the Hubble atom. Visionaries like Ralph Alpha and Robert Herman calculated this very transition, predicting that the relic glow from the universe's birth would suddenly find a clear path forward, a prediction that was later spectacularly confirmed. But the role of neutral atoms went even further. By clearing the fog, they also set the cosmic stage for everything to come. For nearly 400,000 years, the intense pressure of radiation had been pushing against matter, preventing it from clumping together under its own gravity. Now, with light gone, that pressure vanished. The universe was plunged into darkness, a quiet, transparent expanse where neutral hydrogen gas could finally begin to feel the subtle tug of its own gravity. The seeds of structure, those tiny density variations from the primordial fire, could now begin to grow. In the profound silence left by light's departure, the first whispers of galaxies were born. This ancient light still washes over us today, a cosmic whisper from the dawn of time. It is the cosmic microwave background radiation, the direct and tangible echo of light's great escape. After it broke free during recombination, That initial flash of liberated photons began an epic journey across an ever-expanding universe. Stretched by the expansion of space itself over billions of years, their once searing energy has cooled into a faint, cold glow in the microwave part of the spectrum, just a few degrees above absolute zero. This radiation is not coming from one point in the sky. It fills the entire cosmos, a nearly uniform background hum that is the oldest fossil we will ever observe. Its discovery in 1965 was a stroke of serendipity. Radio astronomers Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a persistent, mysterious noise in their giant horn antenna. They pointed it at the sky and the hiss was there. They pointed it at New York City and the hiss was there. They even famously cleaned out a pair of pigeons nesting in the antenna, but the annoying static remained constant in every direction. They had not found a faulty instrument. They had accidentally stumbled upon the faint, cooled remnant of the universe's fiery birth, the first direct evidence for the Big Bang model. This cosmic snapshot, however, is not perfectly smooth. Embedded within its near uniformity are tiny, precious variations, anisotropies that appear as minute temperature differences, mere millionths of a degree. These are the imprints of those original density seeds from the primordial plasma, the gravitational blueprints for everything that would follow. Space missions like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have meticulously mapped these subtle fluctuations, creating a baby picture of the universe. The patterns in this light tell us the universe's exact age, its composition, and its geometry. They confirm that the faint ripples in that early sea of matter and energy were destined, under the relentless pull of gravity, to become the vast cosmic web of galaxies and clusters we see today. The cosmic microwave background is more than an echo. It is the ultimate witness, a fossilized moment of liberation that continues to tell the story of how our structured cosmos emerged from a formless, brilliant fog. The very physics that trapped light also held the secret to its release. This process is known as Thompson scattering. In the early universe's dense plasma, a photon's existence was a series of frantic, random deflections. Picture a single photon, a tiny packet of light energy trying to travel in a straight line. Almost instantly, it would collide with a free electron. The photon would not be absorbed and destroyed, but its path would be violently altered, its energy slightly shifted, and it would be sent careening off in a completely new direction. This was not a rare event. In that searing hot fog, the mean free path of a photon, the average distance it could travel before another collision, was incredibly short, perhaps only the width of a city block on the cosmic scale. The cross-section for this interaction, a measure of how big a target each electron presented, was substantial. With so many free electrons buzzing around, the universe's opacity was nearly total, creating the brilliant, impenetrable prison walls. The key to the Great Escape lay in a fundamental change to the electrons themselves. As the universe cooled and recombination began, these free electrons were captured by protons to form neutral hydrogen atoms. An electron bound within an atom is a profoundly different entity for a passing photon. Its effective size, its scattering cross-section, shrinks by an astronomical factor. It becomes almost invisible to light. The frantic scattering, which had occurred trillions of times over hundreds of millennia, simply stopped. The Saha equation, a powerful piece of physics developed by Meghnad Saha, beautifully describes this tipping point. It quantifies the ionization fraction, calculating the precise moment when the population of free electrons drops so low that the plasma becomes a transparent gas. The opacity of the cosmos collapsed, and the mean free path of a photon suddenly stretched to nearly infinity. This was the decoupling, the moment radiation and matter went their separate ways. The universe did not just cool into clarity, it underwent a fundamental phase transition dictated by the simple, elegant rules of Thompson's scattering, forever altering the destiny of every photon within it. Light's freedom did not arrive in a single, brilliant flash, but as a gradual dawn over cosmic millennia. Decoupling, the moment light broke its chains, was not an instant but an era, a slow-motion escape that unfolded over roughly 10,000 years. At its heart lies the concept of redshift, a measure of how much the universe has stretched since that ancient time. The pivotal moment corresponds to a redshift of around 1,100, a number that signifies the universe was about 1,000 times smaller and infinitely denser than it is today. As the cosmos cooled past 3,000 Kelvin, the process of recombination began its work, steadily draining the sea of free electrons. With each passing century, the density of these charged particles plummeted, and the path ahead for every trapped photon grew exponentially clearer. A photon that could only travel a few kilometers before a collision might, 1,000 years later, be able to travel 1,000. The universe was not a light switch being flipped, but a thick, blinding fog slowly and steadily lifting. This entire transition period created what scientists call the last scattering surface, a spherical shell embedded in time from which the cosmic microwave background appears to originate. It is not a literal wall, but a statistical moment, the point from which most of the ancient photons we detect today began their unimpeded journey. Detailed computer simulations of this process reveal an even more nuanced picture. Decoupling was not perfectly clean. A tiny fraction of photons experienced one final, fleeting interaction with matter even after the main event, a residual scattering that left a subtle but crucial imprint on the light itself. This final interaction polarized the cosmic microwave background, giving its light a preferred orientation that acts like a fossilized record of those very last moments of struggle. This polarization, a key target for modern observatories, tells us about the dynamics of the plasma in its final throes. Understanding this extended timeline is not just a historical curiosity. It is absolutely critical for interpreting the minute details we see in the cosmic microwave background today. The slight blurring caused by the gradual decoupling affects how we measure the universe's age, its composition, and the precise nature of those initial density seeds. This 10,000-year dawn reminds us that the most profound transformations of the cosmos are not explosive singularities, but patient, epoch-spanning processes where the universe meticulously rewrites its own laws of physics. That single equation, scrawled on a page in 1920, held the mathematical key to the universe's great transformation. It was the work of Indian astrophysicist Meghnad Saha, a formula born from studying stellar atmospheres that would one day decode the cosmos's own birth cry. The Saha ionization equation does something profound. It describes the precise balance in a hot gas between ionized atoms, which are broken apart into free electrons and nuclei, and neutral atoms, which are whole. It calculates the ionization fraction, telling you exactly what percentage of the gas is a charged plasma and what percentage is a transparent neutral gas, all based on temperature and density. When cosmologists applied this powerful tool to the early universe, they could rewind the expansion and cooling to find the exact moment of change. The math revealed a tipping point. Above a temperature of about 3,000 Kelvin, the thermal energy is so intense that it smashes any atom that tries to form. The equation shows the universe is almost entirely ionized, a perfect prison for light. But as the temperature drops below that critical threshold, the balance of power flips with stunning speed. The Saha equation predicts a rapid, runaway process. The formation of the first neutral atoms makes it easier for the next ones to form, draining the sea of free electrons in a cosmological cascade. It was not a gentle transition, but a swift and decisive phase change for the entire cosmos. This mathematical prediction aligns perfectly with what we observe. The Saha equation tells us that decoupling happened when the universe was only about 380,000 years old, at a redshift of roughly 1,100. This is the exact epoch from which the cosmic microwave background radiation originates, a theoretical calculation made decades before the background radiation was discovered correctly foretold the properties of our oldest cosmic fossil. The equation is a stunning bridge connecting the microscopic world of atomic binding energies to the grandest scale of cosmic evolution. It demonstrates that the liberation of light was not a random accident or a mystical event. It was an inevitable consequence of fundamental physics, a destiny written into the laws of thermodynamics that unfolded with perfect, predictable timing. The universe cooled, and the equations knew exactly when the prison doors would swing open. This invisible shell surrounding us is the ultimate time machine. It is called the last scattering surface, a fossilized horizon from which the cosmic microwave background appears to emanate. Think of it not as a solid wall, but as the final, fading echo of a great cosmic event. Every single one of the ancient photons that we detect with our telescopes began its long journey to us from somewhere on this immense spherical shell. The distance to this surface is almost incomprehensible, about 46 billion light-years away. This vast number is not a measure of how far the light has traveled through a static space, but a testament to the relentless expansion of the universe itself during the billions of years the photon was in flight. Space stretched, and in doing so, it stretched the very origin point of the light to a staggering remove. The shell also has a thickness, a depth that corresponds directly to the 10,000-year period over which decoupling gradually occurred. This is not a perfectly sharp moment, but a fuzzy epoch, a transitional era forever frozen in the light we observe. The temperature and polarization patterns we see are not painted on a flat canvas, but are imprinted throughout this thick, spherical layer of space-time. By analyzing these subtle variations, astronomers are essentially doing cosmic archaeology, peeling back the layers of this fossilized horizon. The hot and cold spots, those minute temperature differences, are the direct descendants of the primordial density fluctuations from the plasma era. They are the gravitational seeds for all future structure, magnified and preserved on the largest possible canvas. The specific size and distribution of these spots act as a cosmic ruler, allowing scientists to measure the geometry of the universe itself. Is space flat or is it curved? The patterns on the last scattering surface provide the definitive answer. They also carry the faint imprint of the first sound waves that ever rippled through the cosmos, the baryon acoustic oscillations that were frozen in place when light escaped. This surface is therefore far more than a relic. It is a dynamic snapshot, a complex data set that tests our most fundamental ideas about cosmic inflation and the mysterious nature of dark matter. It is the universe's own time capsule, meticulously preserving the precise moment its prison walls fell and light first tasted freedom. Light's escape was the starting gun for the cosmos to build itself. For nearly 400,000 years, the intense pressure from that trapped radiation had been pushing back against gravity, preventing matter from clumping together. Every time gravity tried to pull a cloud of gas inward, the relentless push of photons would shove it right back out. It was a cosmic stalemate, a perpetual tug of war where no structure could ever form. But the moment light broke free, that opposing pressure vanished almost completely. The universe was suddenly plunged into a state of profound gravitational quiet. For the first time, matter could finally listen to the whispers of gravity. Those tiny, random variations in density from the primordial plasma, the invisible seeds we mentioned earlier, were no longer being suppressed. They could now grow. A region that was ever so slightly denser than its surroundings began to pull in a little more gas from the area around it. This made it even denser, which increased its gravitational pull, allowing it to draw in even more matter. This runaway process, known as gravitational collapse, could finally begin in earnest. The Dark Ages had commenced, a period where the universe was filled with neutral hydrogen gas, utterly dark to our eyes, yet humming with the silent, patient work of gravity. It was within this expansive darkness that the first grand structures, the blueprints for galaxies and clusters, began their slow, deliberate coalescence. The cosmic microwave background holds a frozen record of this very moment of release. The hot and cold spots we see in that ancient light are the imprints of those final, trapped sound waves in the plasma, the baryon acoustic oscillations. Think of these as the fossilized ripples from a cosmic pond, the last vibrations of the photon baryon fluid before it fell silent. When light decoupled, these oscillations froze in place, leaving behind spherical shells of slightly overdense matter. These overdensities became the preferred locations where gravity would later do its work, the cosmic nurseries for the very first protogalaxies. So the Great Escape did far more than just clear a fog. It handed the universe over to gravity, transforming it from a formless, brilliant fireball into a structured, evolving cosmos. The chains that fell from light became the foundations for everything we see, from the smallest star to the largest supercluster of galaxies. An invisible architect was already at work, shaping the cosmos even before light broke free. This mysterious force was dark matter, a substance that fundamentally does not interact with light at all. While the searing plasma of protons and electrons was locked in a violent dance with radiation, dark matter remained aloof. It was completely immune to the intense pressure of photons, unaffected by the electromagnetic prison that held ordinary matter captive. This unique property gave it a profound head start. While baryonic matter, the stuff of atoms, was being pushed and scattered by light, dark matter could quietly begin to gather. It responded only to gravity, and so it started to pool ever so slightly within the tiny density fluctuations sown in the primordial universe. These pools of dark matter became the first gravitational wells, the earliest seeds of structure in an otherwise formless expanse. They were subtle dips in the fabric of space-time, waiting patiently for their moment. When recombination finally occurred and the radiation pressure vanished, ordinary matter was suddenly free to move. The neutral hydrogen gas, now liberated from the photon's push, immediately felt the gentle, persistent tug of these pre-existing dark matter concentrations. Baryons began to flow like water into these invisible basins, accelerating the process of structure formation dramatically. Without this dark scaffolding, the universe would have been a much slower, more barren place. The gravitational pull from ordinary matter alone was too weak to overcome its own thermal motion quickly. Galaxy formation might have been delayed for billions of years, or perhaps never reached the grand scale we observe. Sophisticated computer simulations starkly illustrate this difference. A universe without dark matter shows a pitiful delay in creating the first stars and galaxies, a cosmic landscape that remains simple and diffuse for far too long. But with dark matter's guiding hand, the neutral gas left behind after light's escape had a ready-made blueprint to follow. It fell into the waiting dark matter halos, compressing and cooling until the first stars could ignite, ending the cosmic dark ages. So dark matter was more than a passive bystander in light's great journey. By establishing the gravitational foundations for all future structure, it directly influenced how light would later propagate through the cosmos. The very first stars that flooded the universe with new light did not ignite at random. They were born within the invisible, nurturing cradle of dark matter, the silent architect that built the stage for light's triumphant return. But beneath this grand cosmic narrative lies a hidden, microscopic world. The frantic dance of capture and release between light and matter was governed by the strange rules of quantum mechanics. At this fundamental level, photons and electrons were not just particles, they were excitations in quantum fields interacting through fleeting, ghostly exchanges. In the searing plasma, a photon did not simply bounce off an electron like a ball. Instead, the photon and electron interacted by briefly trading a virtual particle, a ghostly intermediary that existed for a vanishingly small instant, just long enough to transfer energy and momentum. This process, described by the theory of quantum electrodynamics, happened with incredible frequency. The universe was so dense that these quantum scatterings kept photons in a state of constant, chaotic conversation with the charged particles around them. They were in what physicists call local thermal equilibrium, a shared state of energy where light and matter were perfectly coupled, unable to escape each other's influence. The entire opaque fireball was a quantum system in violent, perfect balance. As the universe expanded and cooled, this balance was shattered. The formation of neutral hydrogen atoms was a quantum mechanical event in itself, with electrons settling into specific, discrete energy levels around protons. This reorganization of matter had a dramatic effect on the quantum landscape. The probability of those fleeting virtual particle exchanges plummeted. The effective target that an atom presented to a photon became astronomically smaller than that of a free electron. The constant quantum chatter that had trapped light for eons simply faded into silence. Photons were no longer prisoners of local thermal equilibrium. They began to behave as free quantum fields, their wave functions propagating through the vastness of space without interruption. We can model this transition using the tools of quantum statistical mechanics, which describe how large ensembles of particles change their collective behavior. The mathematics shows that decoupling was not a single line crossed, but a statistical shift in probabilities. As the density of free electrons dropped, the odds of any one photon having a final scattering event decreased until that probability effectively reached zero. This quantum perspective reveals a profound truth. The moment the universe became transparent was not just a consequence of falling temperatures in a classical sense. It was an emergent property, a large-scale phenomenon born from countless tiny quantum events. The grand story of light's escape, of a cosmos flooding with its first free light, was written in the language of probabilities and cross-sections. The key that unlocked the universe was forged in the quantum realm. The key to light's prison was forged in the universe's very first moments. An unimaginably brief epoch known as cosmic inflation set the stage for everything that followed. In a fraction of a second smaller than any we can measure, the fabric of space itself underwent a period of explosive, exponential stretching. This wasn't the steady, gradual expansion we see today, but a violent, faster-than-light growth that smoothed and flattened the infant cosmos. During this incredible event, the microscopic, jittering world of quantum mechanics was magnified to a cosmic scale. Tiny quantum fluctuations, random pops of energy in the fabric of space-time, were stretched along with everything else, frozen into place as the faintest ripples in density. These ripples became the primordial seeds, the subtle blueprint for all future structure. They were the very same density variations that would later dictate where the first galaxies would form, and critically, how light would finally break free. These imprints from inflation directly influenced the moment of liberation. As the universe cooled toward the epoch of recombination, Those subtle density differences meant that some regions of the primordial plasma were ever so slightly denser and hotter than others. In a denser patch, the frantic dance between electrons and protons lasted a fraction longer, as the higher particle density made it just a bit harder for atoms to form and persist. In a slightly emptier, cooler region, recombination could occur a little sooner. The Great Escape was not perfectly synchronized across the cosmos. It was a global event with local variations, a symphony of transparency conducted by the ancient whispers of inflation. This is why the cosmic microwave background is not a perfectly uniform sheet of light, but is painted with those tiny temperature variations. The hot spots correspond to regions of slightly higher density where light struggled a moment longer to get free. The cold spots are the echoes of emptier voids where the fog cleared just a little bit earlier. Inflation's fingerprints are all over this cosmic snapshot. It made a specific prediction about the nature of these primordial ripples. The theory stated that the fluctuations should be nearly scale invariant. What does that mean in plain terms? It means the pattern of hot and cold spots should look statistically similar, whether you examine a large patch of the sky or a very small one. The fundamental texture of the universe should be the same at all scales. This is precisely what satellites like Planck have observed with stunning precision in the cosmic microwave background. The pattern of variations we see matches the prediction of inflation perfectly. This confirmation tells us that the process which created the seeds for galaxies also meticulously engineered the conditions for light's release. Without this initial period of inflation, the early universe might have been a chaotic, lumpy mess, far too inhomogeneous for a clear, universal moment of decoupling to occur. Recombination would have been a ragged, incomplete process, happening at wildly different times in different places. The cosmic microwave background would be a splotchy, incoherent map, not the finely detailed blueprint we observe. So cosmic inflation did more than just create the potential for galaxies. It engineered a universe where light's prison had a definable key. It ensured that the transition from an opaque fireball to a transparent cosmos was a coherent, observable event, one whose echo we can still detect and decode today. The Great Escape was not a random accident, but a destiny written into the cosmos during its first fleeting breath. Silence and darkness fell across the cosmos. The brilliant fireball was gone, replaced by an immense, transparent void filled with a featureless sea of neutral hydrogen gas. This was the beginning of the cosmic dark ages, a profound interlude that would last for hundreds of millions of years. The universe was now clear, but it was also profoundly dark. The only light was the fading afterglow of the cosmic microwave background, cooling and stretching into invisibility, and the occasional faint whisper of a hydrogen atom shifting its internal energy state. For the first time, there were no brilliant stars, no swirling galaxies, not even a single spark to pierce the overwhelming blackness. This was the direct and necessary consequence of light's escape. By clearing the fog, the universe had eliminated its own primary source of illumination, trading a brilliant prison for an infinite, silent cathedral. Yet within this profound quiet, something crucial was happening. With the pressure of radiation gone, gravity was finally the dominant force. It began its patient, relentless work, pulling ever so gently on the subtle density variations imprinted in the gas. A region that was slightly denser than its surroundings would pull in a little more matter from its neighborhood. This made it denser still, increasing its gravitational pull, allowing it to draw in even more gas. Over millions of years, these whispers of gravity amplified into a slow, cosmic crescendo, gathering the raw material for the first structures in the universe. The Dark Ages were not an empty pause. They were a period of immense potential, a cosmic incubation where the seeds of everything to come were quietly, invisibly beginning to grow. The transparency forged by light's escape was the essential condition for this growth. It allowed the faint ripples of gravity to propagate without being scattered or overwhelmed by searing radiation. It set a stage of perfect stillness, waiting for the first actors to arrive. This deep, universal darkness was the blank canvas upon which the first stars would eventually paint their brilliant light. The darkness was not destined to last. Deep within the gravitational wells sculpted by dark matter, the first stars began to ignite. They did not flicker on one by one, but erupted across the cosmos like a sudden constellation of cosmic beacons, ending the long silence of the Dark Ages roughly 100 to 200 million years after the Big Bang. These were not like the stars we see today. They were the universe's first generation, known to astronomers as population 3 stars, formed from the pristine clouds of pure hydrogen and helium left behind by the Big Bang. They were behemoths, hundreds of times more massive than our Sun. And with that immense mass came ferocious heat and pressure. Their cores burned at temperatures far exceeding those of modern stars, and they lived fast and died young, blazing with a brilliant, intense ultraviolet light. This new, powerful radiation began to do something extraordinary to the universe around it. It started to tear apart the very atoms that had once set light free. The intense ultraviolet photons from these first stars slammed into the neutral hydrogen gas that filled the cosmos. Each photon carried enough energy to rip an electron away from its proton, reionizing the atom and flooding space once again with free electrons and protons. This monumental process is called reionization, and it marked a new chapter for light itself. It was not a uniform wave of change, but a patchy, gradual transformation. Around each of these first brilliant stars, a growing bubble of ionized gas would appear. Within these bubbles, the universe was once again transparent, but not to all light. This time, it was transparent to the higher energy, ultraviolet photons that had been trapped before. As more of these massive stars ignited and then exploded as supernova, their ionizing bubbles expanded and began to merge, like holes forming and connecting in a vast cosmic sheet. Over hundreds of millions of years, these bubbles grew and overlapped until the entire universe was reionized, a process that was largely complete by the time the universe was about 1 billion years old. This second great ionization did not imprison light. Instead, it liberated a new kind of light, clearing a path for the high-energy radiation that would allow us to see the most distant quasars and the earliest galaxies. The first stars did not just illuminate the darkness, they fundamentally re-engineered the cosmos, forging a transparent universe where light could not only travel freely, but could also carry the full story of cosmic evolution across the vastness of space and time. This ancient light is our most reliable witness, and its testimony is etched into the sky with scientific precision. The cosmic microwave background radiation is not a random hiss. It carries the specific, predicted signature of a perfect blackbody. This unique type of spectrum is the unmistakable fingerprint of an object in complete thermal equilibrium, exactly what you would expect from the dense, uniform fireball of the early universe. When the Planck satellite mapped this radiation, it found a blackbody curve of such stunning perfection that it is the most precise match in all of nature. This alone tells us the light was once trapped, boiling in a confined state before being suddenly released. But the story gets even more detailed. Superimposed on this near-uniform glow are the anisotropies, those tiny temperature variations that appear as a speckled pattern of hot and cold spots across the entire cosmos. These are not random imperfections. Their exact size and distribution, measured with exquisite accuracy by missions like WMAP and Planck, act as a cosmic barcode. When we scan this barcode, it reveals the universe's vital statistics, its age, its composition, and the precise moment when light decoupled from matter. The data confirms decoupling happened at a redshift of about 1,100, when the universe was a mere 380,000 years old. This is the observational proof of the Great Escape, a snapshot of the prison walls dissolving. Beyond this fossilized light, other clues are written in the stars. When we look at the light from the most distant quasars, we see a strange pattern in their spectra known as the Lyman alpha forest. The quasar's light, on its billion-year journey to us, passes through countless clouds of neutral hydrogen gas in the vast voids between galaxies. Each cloud absorbs a very specific fingerprint of light, leaving behind a series of dark absorption lines in the quasar's spectrum. This forest of lines is a direct record of the distribution of neutral hydrogen throughout cosmic time. By analyzing this intricate pattern, astronomers can trace the history of reionization, observing how the neutral hydrogen was gradually burned away by the first stars and galaxies. It provides a second, independent timeline that aligns perfectly with the story told by the cosmic microwave background. Even the grand architecture of the universe itself offers corroborating evidence. The immense cosmic web of galaxies and clusters, mapped in enormous surveys, shows a specific pattern of clustering. The preferred distance between giant galactic clusters matches the scale of the frozen sound waves imprinted on the cosmic microwave background, the Baryon acoustic oscillations. This tells us that the seeds for all large-scale structure were indeed sown in the early plasma, and that their growth could only begin in earnest after decoupling, when radiation pressure vanished and gravity took over. These multiple, independent lines of inquiry all point to the same cosmic narrative. The blackbody spectrum, the anisotropies, the Lyman alpha forest, and the large-scale structure together form an unshakable chain of evidence. What began as a theoretical escape story has been validated as empirical fact, a foundational chapter of cosmic history confirmed by the light that first tasted freedom. This cosmic detective story hinges on a powerful dialogue between prediction and observation. Our leading theory of the universe, known as the lambda-CDM model, provides a precise mathematical script for light's great escape. It tells us exactly how the drama of recombination should have unfolded, calculating the specific moment the fog cleared based on fundamental numbers like the density of ordinary matter and the rate of the universe's expansion. Then we look at the evidence, the cosmic microwave background captured by satellites like Planck. We don't just see a pretty picture of speckles, we measure the exact statistical pattern of those hot and cold spots, what scientists call the power spectrum. This pattern is the universe's own fingerprint. The profound achievement of modern cosmology is that the predictions from the theory and the fingerprint from the sky match with breathtaking precision. By tuning the model's parameters, like the baryon density which tells us how much proton and neutron stuff was in the primordial soup, we can make the theoretical curve lie perfectly over the observed data. This is not a vague resemblance, it's a precise fit that locks in our understanding. Even the subtle details, like the preferred size of the spots caused by those ancient sound waves, are reproduced flawlessly by computer simulations that weave together atomic physics and Einstein's general relativity. These virtual universes run the Great Escape over and over, and they consistently generate a cosmic microwave background that looks just like our own. This powerful convergence tells us we are not just telling a good story, we are reconstructing a real historical event. Of course, the dialogue continues. There are intriguing tensions like the ongoing debate over the Hubble constant. which measures how fast the universe is expanding today. Different methods yield slightly different answers, creating a puzzle that cosmologists are urgently working to solve. Yet it's crucial to understand what this tension means. It doesn't overthrow the core narrative of the Big Bang or light's decoupling. Instead, it refines it, forcing us to look deeper and perhaps discover new physics operating at the edges of our current knowledge. The fact that we can have such a precise argument is a testament to how solid the foundational story really is. The Great Escape of Light is no longer a hypothesis. It is a well-supported scientific consensus, a chapter of cosmic history confirmed by the perfect alignment of our deepest theories with our oldest light. Our very ability to stand under a starry sky and wonder is a direct consequence of that ancient liberation. The moment light tore free from the primordial plasma did more than clear a fog. It set in motion an irreversible chain of events that led directly to us. Without that transparency, the universe would have remained a seething, opaque fireball forever. Stars could never have ignited within that brilliant chaos, their nuclear furnaces smothered by the relentless pressure of trapped radiation. Galaxies would have had no gravitational seeds to grow from, no quiet darkness in which to coalesce. The cosmic dark ages, that essential period of quiet gestation, would never have begun. Every planet, every molecule of water, every potential cradle for life was contingent on that first, fundamental clearing of the air. We are here because the universe cooled and went quiet, allowing matter to finally build something more complex than a searing plasma. But the significance goes even deeper than our own existence. That same transparency is the very reason we can understand our own origins. Light's escape created the ultimate observational window, a clear line of sight across nearly the entire history of the cosmos. Because those first photons have been traveling unimpeded for billions of years, our telescopes act as time machines. We can point them into the deep black and catch the faint, cold whisper of the cosmic microwave background, that fossilized snapshot of the universe at 380,000 years old. We can trace the light from the most distant quasars as it journeys through the thinning gas of the reionization era. Every galaxy we catalogue, every supernova we analyze, is a message sent through the clear vacuum that light's escape made possible. The event that freed light also forged the tools for its own discovery. It gave us a cosmos we can not only inhabit, but also one we can observe, measure, and ultimately comprehend. Our quest to understand the Big Bang, the formation of elements, and the nature of dark matter all rely on this single, pivotal transition. The universe became transparent, and in doing so, it created both the stage for life and an audience to witness its own magnificent story. Clearing up a few common myths can sharpen our view of this cosmic dawn. Many people hear the term Big Bang and picture a giant explosion erupting at a single point in an empty void. But the reality is far stranger. The Big Bang was not an explosion in space. It was the rapid expansion of space itself, everywhere at once. There was no center, no edge. Every single point in our entire observable universe was once crushed together in that initial state of immense density and heat, and then space itself began stretching, carrying matter and energy along with it. This crucial distinction changes everything about how we imagine the early cosmos. Another persistent myth is that the moment light escaped was a single, brilliant flash. We have spoken of decoupling as an era, a process spanning thousands of years. It was not a light switch being flipped on, but a cosmic fog lifting with infinite patience. And while we call the time after this the Dark Ages, it was not a period of absolute blackness. The entire universe was still bathed in the fading, warm glow of the cosmic microwave background. It was a dull, uniform red that would have shifted to infrared and beyond. invisible to our eyes but very much present, a final ember of the primordial fire. Even the role of dark matter is often misunderstood in this story. While it is true that dark matter did not interact with the light directly, to say it played no role is a profound mistake. Its silent, gravitational pull had already begun sculpting the cosmos, creating the deep wells into which ordinary matter would flow the instant light set it free. It was the invisible architect whose blueprints were essential for the next act. Each of these clarifications is more than just a technical correction. They are vital to understanding how science reconstructs this ancient history. We take these complex, sometimes counterintuitive ideas and test them against the evidence, from the perfect blackbody spectrum of the background radiation to the large-scale structure of galaxies. By dispelling the simpler, more dramatic myths, we open ourselves to the true, grand narrative of the cosmos, a story of gradual, majestic transformations governed by the relentless laws of physics. The faint whisper of the cosmic microwave background still has profound secrets to tell. A new generation of observatories is now turning its gaze to this ancient light, armed with technology sensitive enough to read its most subtle messages. Projects like the Simons Observatory and the ambitious CMB-S4 are not simply building bigger telescopes. They are creating vast arrays of ultra-sensitive detectors, positioned in the pristine, dry air of the Atacama Desert and the South Pole to minimize atmospheric interference. Their primary target is the faint polarization of the cosmic microwave background. You can think of polarization as a specific direction or a preferred orientation imprinted on the light itself. One particular pattern, known as B-mode polarization, is the holy grail of this search. It is considered a potential signature of primordial gravitational waves, ripples in the very fabric of space-time that were generated during the universe's violent inflationary birth. Detecting this signal would be like hearing the echo of the Big Bang itself, providing our first direct evidence for cosmic inflation and revealing physics at energy scales 1 trillion times higher than any particle collider on Earth can reach. But the quest does not end there. These advanced experiments will also meticulously study what are called secondary anisotropies. These are tiny distortions in the background radiation imprinted not during its escape, but much later, as the ancient light passed through the growing cosmic web of galaxies and clusters. By analyzing these subtle effects, scientists can trace the history of the universe's reionization in exquisite detail, and even probe the mysterious properties of dark energy, the force accelerating cosmic expansion. The incredible precision of these new maps may even allow us to weigh the neutrino, the ghostly particle that floods the cosmos, and place new constraints on the nature of dark matter itself. Every refinement in our measurement of this fossil light brings us closer to understanding the precise conditions that allowed light to shatter its chains. The great escape that cleared the cosmic stage billions of years ago continues to illuminate the deepest frontiers of physics, turning the universe's oldest light into a beacon for its newest discoveries. These cosmic events can feel abstract, but their essence is mirrored in our world. Picture a dense, chilling fog at daybreak. For hours, you cannot see more than a few feet ahead, the world reduced to a gray, swirling haze. This is the universe before its great transformation, a brilliant but opaque prison. Then, as the sun climbs, its rays begin to pierce the mist. Patches of blue appear, and the fog thins until the entire landscape is bathed in clear, golden light. This is the moment of decoupling. The photons are those first rays of sunlight, and the clearing fog is the sea of free electrons vanishing as they bind into atoms. The universe did not simply cool, its fog lifted, or step into a different scene, a room packed with people all moving chaotically. You try to cross from one side to the other, but every time you take a step, someone bumps into you, sending you off in a new direction. You are trapped in a human traffic jam, just like a photon in the early plasma. Then a signal is given, and everyone in the room finds a chair and sits down. The path ahead is suddenly clear. You can walk in a straight line from one wall to the other without a single interruption. The people sitting down are the newly formed neutral atoms. Their decision to settle instantly transforms the room from an impenetrable crowd into an open space, allowing for free and direct movement. Even the process of recombination itself has a beautiful earthly parallel. Think of a pot of water coming to a rolling boil. Bubbles of steam rise and pop, creating a turbulent, cloudy chaos. Light passing through this churning water would be scattered in every direction. Now watch as you turn off the heat. The boiling stops, the bubbles vanish, and the water becomes still and perfectly clear. The transition from a searing plasma to a neutral gas was a cosmic version of this shift, a phase change where the entire universe settled from a violent boil into a tranquil, transparent state. These are not perfect comparisons, but they are vital bridges. They translate the mathematics of scattering cross-sections and ionization fractions into human experiences of fog, crowds, and boiling water. By grounding the cosmos in the familiar, we can truly feel the weight of that great escape, the profound quiet that fell when light finally won its freedom, and the universe opened its eyes for the first time. This delicate balance of forces was the universe's first great standoff. For nearly 400,000 years, the cosmos was locked in a stalemate between two fundamental powers, gravity and radiation pressure. On one side was gravity's relentless inward pull, constantly trying to draw matter together. Pushing back with equal ferocity was the intense outward pressure from the seething sea of trapped photons. Every time gravity attempted to compress a slightly denser patch of the primordial plasma, the radiation pressure would act like a powerful spring, shoving it back outward. This created a rhythmic pulse that reverberated through the entire fiery cosmos, a series of compression and rarefaction waves known as baryon acoustic oscillations. Picture a sound wave traveling through air, where regions of high and low pressure alternate in a regular pattern. The early universe was filled with these cosmic sound waves, but they were frozen in place, unable to propagate freely through the thick photon baryon fluid. The competing forces created a characteristic scale, a specific distance these waves could travel before the universe cooled and changed everything. This distance is now permanently imprinted on the cosmos. The moment light escaped during recombination, this entire dynamic shattered. The radiation pressure, which had been the dominant opposing force, vanished almost instantly. With that outward push gone, gravity was suddenly unopposed. The stalemate was broken. The rhythmic oscillations froze in their tracks, and the overdense regions, the peaks of those cosmic sound waves, stopped bouncing back. They began to collapse under their own weight, their inward fall no longer checked by the powerful pressure of light. This was the pivotal shift that allowed matter to finally build. The great chains of radiation that fell from light became the scaffolding for galaxies. The silent, patient force of gravity, now the undisputed master of the cosmos, could begin its slow, deliberate work of pulling these density seeds into the vast, dark matter wells that were already waiting. The liberation of light was, in the same instant, the liberation of matter. It was the moment the universe traded a brilliant, uniform fireball for the potential of a structured, complex cosmos, where stars could ignite and galaxies could spin in the vast darkness. While photons were the prisoners of the primordial plasma, other cosmic inhabitants had already won their freedom. Neutrinos, those ghostly particles that barely interact with anything, had broken away from matter in the very first second after the Big Bang, long before light's struggle even began. Trillions of these invisible particles were streaming through the searing hot fog, passing through the frantic dance of electrons and protons as if they were not even there. Their role in the Great Escape was not one of direct intervention, but of silent influence. By adding to the universe's total energy density, neutrinos contributed to the relentless pull of gravity that governed the expansion rate of the cosmos. A universe with more radiation expands and cools faster, and these free-streaming particles were a key part of that radiation-dominated era. They helped set the tempo for the cosmic cooling that would eventually make recombination possible. Other elusive actors were also at play. Dark matter, as we've seen, was gathering silently in the background. Hypothetical particles, relics from even higher energy physics, may have also been present, each contributing their own subtle push or pull to the unfolding drama. To fully understand the precise moment the fog cleared, cosmologists must account for this entire particle inventory. The tiny fluctuations we see in the cosmic microwave background are exquisitely sensitive to the number of relativistic species present in the early universe. By matching our theoretical models to the observed patterns, we can effectively count the number of light particles that were free streaming at that time, with neutrinos leaving a distinct, measurable imprint. The story of light's escape is not a solo performance but a grand cosmic symphony. Every fundamental constituent, from the trapped photons to the ghostly neutrinos and the invisible dark matter, had a part to play. The prisoners broke free only when the stage, meticulously set by every particle in existence, was finally ready. This cosmic birth of vision is a story humanity has told itself for millennia, long before we knew the physics. The ancient escape of light from a formless fireball mirrors our deepest cultural narratives of emergence from darkness into understanding. From the Egyptian sun god Ra vanquishing the serpent of chaos to Plato's allegory of the cave, where prisoners first glimpse the sun and comprehend true reality, our myths are filled with the struggle for light and clarity. The scientific story of recombination is a modern incarnation of this universal theme, a literal dawn where the cosmos itself stepped out of blinding confusion and into a state where sight and structure became possible. It transforms our understanding of the universe from a collection of random events into a grand, coherent narrative of transformation, one where the physical laws themselves act as the authors of liberation. We are not just observing a cold mechanical process, we are witnessing the universe fulfill a potential for clarity written into its very fabric. This capacity for radical change, from an opaque prison to a transparent expanse, hints at a cosmos that is dynamic and evolving, capable of generating the complex conditions we now call home. Our ability to piece together this story, to look back across billions of years and understand an event that occurred long before Earth existed, is itself a philosophical marvel. It forges a profound connection between human consciousness and cosmic history. Our curiosity is not separate from the universe, it is a product of it, a means for the cosmos to become aware of its own origins and its own epic journey. The very fact that we can ask these questions, that we can detect the faint whisper of the cosmic microwave background and decode its message, rests upon a chain of circumstances of incredible fragility. If the universe had expanded a fraction faster, matter would have spread too thin for atoms to form and stars to ignite. If it had expanded slower, it might have collapsed back on itself in a fiery crunch. The precise strength of gravity, the exact properties of the atom, all had to be tuned to allow for a transparent universe that could later host living, questioning beings. This realization places us in a unique and humbling position. We are not just inhabitants of the cosmos, we are its aware witnesses, the universe's own way of understanding the moment it opened its eyes. The great escape of light is therefore more than a pivotal physical event. It stands as a powerful symbol for knowledge itself breaking free from obscurity. Every time we pursue a scientific discovery, every time we push back the boundaries of ignorance, we reenact on a human scale that primordial cosmic transition. The light that first traveled freely now illuminates not just space, but also the human mind, inspiring a sense of wonder that bridges the gap between the quantum realm and the grandest philosophical questions about our place in the vast, transparent expanse we